I'll share my screen, and hopefully you can see my screen as well. And so I'm going to talk about the Trim Lasso. It's a new method to find sparse solutions. And this is a joint work with Tal Amir and with Ronen Batzri. It's essentially the PhD of Tal Amir. All right. So the problem that we're going to talk about is has various names, but one of them is called the best subset selection problem. It's a fundamental problem in computational mathematics, and here is its formulation. You are given a vector y of n measurements, a matrix A of size n by d, a sparsity parameter k, and your goal is to solve this least squares problem, but you want to find a minimizer that is k-sparse. Okay, so this problem, we'll call it P0. And this problem appears in many, many different applications. In statistics, it's called sparse linear regression. In approximation theory or harmonic analysis or signal processing, Y is typically the samples of a signal that you measured. A is called the dictionary, and its columns are called atoms. These are different base signals, and this problem amounts to approximating Y by a linear combination of K atoms from your dictionary. So it's called the best K-term approximation. And of course, this problem also appears in compressed sensing, and various related problems appear in bioinformatics, machine learning, and more. Okay. And of course, the common case is high dimensional. It's when you measured few observations, n is small, and the dimension of the vector x is large. All right. Typically, the parameter k, how sparse is your vector, is not a priori known. It needs to be estimated. There are many different methods to do so. One of them is just to simply solve the problem for several values of k, and somehow decide either by cross-validation or some other model selection criteria the best value of k. For this talk, I'm going to assume that k was given to us, and we're going to focus on how to solve that simple least squares problem with a given value of k. Okay, and k is typically smaller than the number of measurements and n of the dimension. And now, the key challenge is to find the right support, the k atoms that should be included, because if someone gives me those, the problem just becomes simply squares. This is NP-hard in general. And yet, because this problem is so important, there have been a lot of work, algorithms, theory, lower bounds, recovery guarantees. There are at least 100 methods to try to solve this problem P0, and also a lot of theoretical results, etc. A little bit about how previous works try to tackle this problem. So some works try to greedy choose atoms one by one or several by several. There's a famous paper by Stefan Mala and others, orthogonal matching pursuit. All of these methods are very fast and also easy to program. A few years ago, there was a very nice work by Bertsimas and co-authors from MIT. They devised a method to globally solve the problem by some smart combinatorial search. In some cases, they terminate with a guarantee of global optimality much, much faster than exhaustive search. However, for various instances of the problem, their code may run days, weeks, months. This is an example on a relatively small problem that took us several days to run their code until getting that global optimality. Perhaps the most common methods, and this is also what the concept that we're going to pursue, is to add some penalty function to the least squares objective. And the most common one is called the L1 or the Lasso or basis pursuit. It's just the sum of the absolute values of the x's. And this promotes sparse solutions, and then this problem is also convex, etc. All right. In terms of theoretical guarantees, there's been a lot of them. I'm not going to review all of them. I hope some people are familiar with these notions. There is notions of coherence of the dictionary, restricted isometry property, null space property, etc. The bottom line is that under some conditions, some of these current methods are optimal. They recover the correct solution, even though the original problem is NP-hard. And if you're a newcomer to this field and you've seen so much work, you can think that maybe the problem has been solved. There's not much left to do. And what I'm going to try to convince you today is that the answer is no. There is a lot of room for improvement, and I'll show you what we've been doing on this topic. So the key issue is that on challenging instances, when you have few observations, when the sparsity is large, it's not extremely sparse vectors, essentially all previous methods output far from optimal solutions or run forever, okay? And let me illustrate that on a quite small problem by today's standards, a matrix of 100 by 800, just Gaussian entries. We generated for different sparsity levels a k-sparse vector x, also with Gaussian entries. We compute ax, add some noise. This is our vector y. And now given y, a, and the sparsity k, we're trying to recover x. And we're going to run different algorithms, and we're going to check if they were able to just find a reasonable solution to the least squares problem. Just look if the residual is smaller than the residual of the original vector, okay? This is kind of just to see if they were able to, from an optimization point of view, to solve the problem. So here I'm increasing the sparsity. As I'm increasing the sparsity, the problem becomes more difficult. And what we can see here, this is the lasso. And we see that actually the lasso, its values are above 1, means that essentially it can really solve the problem only for very small sparsities, less than 16, let's say, okay? Here are two other methods which work much better. One is iteratively reweighted least squares. The other one is iteratively reweighted L1. They're able to find good objective solutions with good objectives up to higher values of K. The method that we found works perhaps the best is called iterative support detection. It's a greedy method that tries to find the correct support. And what I'm going to show you today is a method that we developed that in terms of finding solutions with small objectives, it's this red curve, okay? And let's focus for a minute on this sparsity level 36. This is a bit misleading. The y-axis here is the average error over many realizations. What I'm showing you here is that at a sparsity level of 36, here I'm showing you actually now the reconstruction error with respect to the true vector x0. And as you can see, some instances, those that are here, I don't know if you can see, but both our method, which is called GSM, and ISD fail. But all of the instances here on the left are cases where we got very small error, whereas the next best competing method was unable to get a good estimate of the original vector x0. Okay, so now I'm going to, in the rest of the talk, I'm going to describe how we were able to get these results. Okay, so the approach we're going to take is one that adds a penalty to the least squares objective. And what would we like to have from this penalty? We would like, first of all, this penalty, we would like it to depend explicitly on the sparsity k that we are looking for. And we would like this penalty to be a good approximation to the L0 constraint. In particular, we would like that if we take the penalty parameter lambda to infinity, we would recover the solutions of the original problem, okay? And it's very important, we want this penalized problem to somehow be, quote unquote, easy to optimize, maybe smooth, differentiably smooth, and things like that. So we don't want to get stuck on bad local minima. Now, this is where the Trim Lasso comes into play. We invented it, but we then found out that several other people were ahead of us. So the Trim Lasso penalty is defined as follows. For any vector x, you penalize, you sort its coefficients from largest to smallest, and instead of penalizing all of them, you just penalize the smallest ones. The first top k, you don't penalize at all, okay? So it turns out that this penalty was proposed by several different groups. One is Wang in 2015, and then there is a group by Goto et al. In 18, and also the group by Bertsimas et al. From MIT. They also coined it the Trim Lasso, and this is the term that we're going to use. All right. So if you're penalizing the tail of a vector x, you can think about either penalizing the least squares objective, or just with a square, or just penalizing it without a square. These are different optimization problems, and so in some cases, one is easier to optimize than the other. And this formulation raises several questions that we're going to try to address. One is, what is the relation between these optimization problems to the original best subset selection problem? Second, what values of lambda should we work with? And third, how do we actually going to optimize this problem, okay? So our contribution has several parts. One is, two of them are theoretical and one is more algorithmic. On the theoretical side, I'm going to show you an explicit relation between the original problem P0 and these Trim Lasso regularized problems. We'll derive theoretical recovery guarantees if you're solving this Trim Lasso problem. And finally, we're going to derive a practical method to actually optimize this Trim Lasso objective. And this will be actually by introducing a different penalty that is a surrogate penalty that is infinitely smooth, infinitely differentiable, and easier to optimize. All right. So let's start with the relation between the Trim Lasso penalty and the original problem P0. So it turns out that you can define two thresholds, lambda bar and lambda b. And if lambda is larger than one of these thresholds, then the solutions of the relevant problems are k-sparse, okay? So in simple words, if lambda is large enough, and we can compute it explicitly given the matrix A and the vector Y, then global minima of Trim Lasso penalized objectives are solutions of the original problem P0, which is a good thing. We can just try to solve these Trim Lasso objectives instead of solving P0, okay? The second theoretical result is related to sparse recovery guarantees. Suppose that indeed the vector y that we observed is equal to ax0 plus e. E may be some measurement error, and x0 is approximately k-sparse. And the question is, can we accurately estimate x0 by solving, let's say, the power 1 Trim Lasso objective, given y, a, and the sparsity parameter k? And the answer is that, first of all, we need to assume something about the matrix A. So we assume a standard notion in compressed sensing, a restricted isometry property. In our case, it has mixed norms, L2, L1. And the theorem that we're able to prove is that if you have some optimization problem which solve this non-convex optimization and is able to find a solution whose objective is smaller than that of the original x0 if you project it to a k-sparse vector, then you're guaranteed to be close to x0. Okay, and the L1 error guarantee that we have has two terms. One is some constant times the norm of the error, the measurement error we had. And the other one is another constant times how sparse was the original vector x0. Tau k of x0 is exactly the residual L1 norm of x0 beyond its k largest coefficients. If x0 was k sparse, this quantity on the right-hand side is exactly 0. And the bottom line from this theorem is that you can well approximate your original vector x0 by solving these Trim Lasso objectives. The key point is that you can do it at values of lambda which are smaller than those where the global minimizer was k-sparse. In other words, you can solve maybe an easier problem and still get accurate vectors. And of course, if lambda is smaller, then hopefully this problem is easier to optimize. Okay? So to conclude the theoretical part, I hope that in the short time I had, I was able to convince you that optimizing with a Trim Lasso is a promising approach to try to solve the original problem P0. All right, so now the question comes about how do we actually optimize such an objective in practice? And there have been at least 3 different methods, one by Goto, one by Bertsimas. Each one of them.
That we have to sacrifice the commutativity of multiplication. Such a world exists, a world of quaternions, and it is connected and responsible for several phenomena. And
can you repeat the question? I was unable to. Hello?
I don't think that there was a question. Please continue.
Okay. In any case, there are several methods proposed to try to optimize this objective. They all work well at the easy problems where the sparsity is small, and they empirically all fail to find good solutions at more challenging instances. And I think, at least from our perspective, one of the reasons for this failure is that, let's think about this penalty tau k. Okay, I mean, ax minus y, I'm missing a square here. Ax minus y squared is convex, differentiable, everything is nice. But what about this tau k of x? It's the sum of the absolute values of the smallest coefficients. So if you look at its gradient and you change in x, let's say one of the large coefficients, the gradient is 0. And if you change one of the small coefficients, the gradient is either +1 or -1. So the gradient of this tau k is not a smooth function. It's not differentiable. It's either 0 or +1 or -1. And it's difficult to optimize functions like this. What I'm going to show you is a very different approach to do it, and to motivate it, and I'll show you that this approach gives better solutions to P0, and to motivate it, I'll rewrite this Trim Lasso in a different formulation. You can think about this Trim Lasso as the following minimizer. You have your vector x, you choose any subset of size d minus k, look at its sum, and tau k of x takes the subset where the sum is smallest, okay? It's a hard assignment. You have choose d minus k possible subsets. Each one has a sum. You take the one with the smallest value, okay? Now, if you knew the support, that's a great penalty, okay? We showed earlier that if you take this penalty and multiply it by a large enough parameter lambda, you get back solutions of the original problem. But if you don't know the penalty, the support, and you're trying to find it in the course of the optimization, then perhaps choosing only one subset is not optimal. And we were motivated by a well-known function in neural networks, in multi-class classification, in machine learning. It's called the SoftMax function. It's widely used in learning neural networks and other multi-class problems. And it replaces a hard assignment by a soft assignment. And we're going to do something similar, but for vectors. We're going to look at this penalty function. It goes over all possible subsets. For each of them, computes their sum, takes an exponent, and then takes the sum of all of those and takes a log. We call this function generalized soft min, okay, so GSM in short. And this function has some very appealing properties. First of all, it's infinitely differentiable in the function of absolute value of x, okay, which is a good thing. The parameter gamma controls how smooth it is. We'll show that explicitly in a minute. And importantly, for any finite value of gamma, this sum takes into account all possible subsets of size k. So you're not tied to any specific subset, and this is important during the optimization process. Okay, so what we're proposing, now some other important properties about this penalty is the following. If you take the parameter gamma to infinity, you recover the Trim Lasso. Whereas if you take the parameter to 0, you get the original L1 penalty. Okay, so this parameter gamma allows you to tune between a convex problem with the L1 penalty and the Trim Lasso penalty, which is the one that we would like to solve. So instead of solving the Trim Lasso objective, we propose to solve a sequence of problems with tau kx, the Trim Lasso, replaced by this generalized soft min penalty. And we're going to start from easy problems where gamma is small and slowly increase, and we're going to trace the path of solutions. This is called homotopy. So this is our proposed approach. When gamma equals 0, we start from a convex problem, so we know its exact solution, okay? And then we slowly increase gamma. We have some theory about how to do that. I won't have time to go into it. But at each new value of gamma, we start from the solution we found previously. Now, to solve such problems, there are still two issues. One, it's still non-convex, so we need, even though now this penalty is infinitely differentiable, it's still non-convex. For that, we propose a majorization minimization scheme, which essentially linearizes things, and we're going to solve a sequence of convex problems instead. I'm not, I'll see how much time I have for it. And the other challenge is that, remember the formula for tau k? This is the formula for tau k gamma. It involves an exponential number of terms. So we're going to have to find a method to compute this sum and also the gradient of tau k gamma in a reasonable time and with good accuracy. So these are the two challenges that remain to make this approach feasible. And first of all, with respect to the majorization minimization, again, the idea so here is this is the function that is related to the gradient of tau, which also involves an exponential number of sums, okay? And it turns out that if you look at this function, then it is called it's a majorizer of our original function tau k gamma, and in our majorization minimization scheme, we replace this by its majorizer. I won't go into the details, but the bottom line is that we're able to solve this problem by solving a sequence of L1 type problems, because the equation inside this rectangular box is just a weighted L1 problem where the weights depend on our previous solution. But the key point is that this problem inside the box is convex, it's easy to solve, and this is our approach to solve it. I'll say a few words about how we compute this and its gradient. So, as we've said, naive computation would be extremely slow and thus infeasible. But actually, the problem is even more difficult. Remember that when gamma equals 0, the right-hand side is the lasso, but we want to take larger and larger values of gamma. As we take larger and larger values of gamma, we're computing not only an exponential number of sums, but each of them has x minus gamma times something, and these sums, some are small, some are large. With a naive implementation, this is highly numerically unstable. And again, I'm not going to go into the very intricate details, but so first of all, if you think about it a bit, you'll be able to find a simple recursion formula to compute this in polynomial time. I can assure you that formula is not stable. You need to work quite hard and do various non-trivial things in order to devise a recursion scheme that has practical polynomial time and is also numerically stable, that the exponents and the logarithms don't explode. And again, I won't have time to discuss, but we developed such a scheme. And in the last 1 minute that I have, I will show some final results on a different example that appeared in this paper by Bertsimas. Here, the problem is more challenging because the dictionary has correlated atoms. Okay, so some of the columns have dot product, which is large, and this makes the finding which columns to choose more difficult. We also took a vector which is k-sparse, but it's non-zero entries. Some are large, some are small. This makes the problem also more difficult. And we added a little bit of noise. And I'm going to say that the method was able to succeed if its relative L1 error was smaller than twice the noise level. And here are the results of various algorithms. As I increase sparsity k, the probability of success recovery goes to 0. On the very left, you see the L1, which is perhaps the most famous method. Then you have the iteratively reweighted L1 and IRLS methods. The next one in pink is this iterative support detection, and in red, it's our method. And you can see that at some sparsity levels, we're able to always recover the vector with other methods. Their success is between 80 to 95%. And the other extreme, there are, let's say, at a sparsity of 40, we're able to, at least 10% of the instances, find the correct solution, whereas other methods, at least in all 100 or 200 simulations we did here, the success rate was essentially 0. In recent months, we were able to even enhance our method further. We can now apply it to much larger problems with tens of thousands of variables, etc. So I'll conclude here by saying that the original problem I talked about, the best subset selection plays a key role in many, many applications. it's a long-standing challenge to be able to solve these instances in practical time. And even small improvements can have a large scientific impact, for example, in identifying which variables affect some disease or things like that. In this work, we developed some theory for the Trim Lasso penalty, as well as a novel algorithmic approach to solve it by a smooth proxy and developing accompanying optimization schemes. This gives state-of-the-art results as good as or better than most current methods that I'm aware of. And there are many additional applications. We're working on some of them. For example, sparse logistic regression, sparse PCA, and many other problems that you add the word sparse in front of them. The manuscript and code are available on Archive and GitHub. And thank you very much.
Thank you very much. Any questions?
בערבון מוגבל מאוד מאוד. רגע, חכי רגע, אני צריכה כאן משהו להוריד לי מלפני העיניים, שנייה.
Okay, so if no further question, let's thank the speaker again. Thank you, Boaz.
Okay, thank you. Thank you all for listening.
And we can let the next speaker prepare.
Okay, Anne, can you start?
Yes, no problem.
Okay, so maybe I'll present Anne. Anne is doing her PhD thesis in Tel Aviv University, and she's going to talk about new twist to finite difference method and the relation to finite elements method. And so, Anne, please.
Okay. Thank you very much for joining this lecture. This work has been done under the supervision of Professor Adi Ditkovsky. And I'm going to talk about, as he mentioned, the relation between block finite difference methods and finite elements. So first of all, a little background regarding the difference methods that will be involved in this work. The finite difference method are the simplest and oldest method, very standard. The main concept is that the solution is approximated by its values at nodes. We are approximating the differential operator by replacing derivatives with a difference quotients. And in the standard method, the same scheme for each grid point is used except near boundaries. So the main advantages and drawbacks of this method, first of all, the main advantages which makes it very largely used method is that it is a fast and very simple implementation. We have an extensive convergence and error analysis since it's a very standard method. And we can get an explicit semi-discrete form, which gives us flexibility in the choice of time-stepping method if needed. And of course, higher order is feasible. As for the drawbacks, for the standard implementation of this method, there is a lack of geometric flexibility, meaning that the method doesn't deal so well with local discontinuities. And as well, local order and grid size changes in order to reflect the local features of the solution. So this is, for example, one drawback that we would like to overcome. So for the block finite difference, this is basically a subtype of finite difference method. So it is based on the same principle, but in that case, the domain is divided into blocks, and each block includes grid points, and on each grid points, there is a different scheme. Two definitions that we will need in order to proceed with the analysis is, first of all, is the definition of superconvergence, where basically the global error is smaller than the truncation error order, and the error inhibition effect, which is a particular type of superconvergence in which the scheme inhibits the accumulation of the error. So this is the two definitions that we will need. And of course, this will be the error inhibition effect that we will look for in our scheme. The main advantages of the BFD method is that we can create an interaction between local truncation error and dynamics of the scheme, which can be exploited in order to reduce the global error. So this is exactly the effect that we would like to reproduce. And we can make the implementation of boundary conditions for higher order easier in some cases. The drawbacks, they are not yet known, since we will establish an equivalency between the BFD and the finite elements method that I'm going to present in short. So the main concept of the finite elements method is that the domain is divided into elements, and we are looking for an approximation of the exact solution in terms of linear combination of shape or basis functions. Those functions are usually taken as polynomials, and that's what we will do as well. The global residual is orthogonal to all test functions. This is how we get the linear equation system to be solved. And we will use the Galagi method, which basically take the test function and the basis function to be the same. The specific finite elements methods that we will look into is called the discontinuous Galerkin method. But for the FE method, the general type, we have the advantages of geometric flexibility, compatible with high order, and HP adaptivity. As far as the drawbacks are concerned, naturally the semi-discrete scheme is implicit, which reduces the efficiency for explicit time integration. But the discontinuous Galerkin method overcomes some of those drawbacks. So this is a class of finite elements methods, but in that case, we use a discontinuous polynomial space used as a basis function space. The stability is enforced through numerical flux, since at the inter-element boundary, we have a lack of consistency between the solution from every side of the boundary. So we use a numerical flux in order to make it consistent. And the numerical solution is discontinuous between elements as a result. So the main advantages of the DG method, which has been very widely developed in the last few years, the advantages is that it possesses a local data structure, meaning that one cell communicates only with its neighbor. And this makes the implementation of parallel computing easier. And it is explicit in time, and we will see it in our example. So the model problem that we took into consideration in order to do our first analysis is a time-dependent problem of the first order. And on the other side, the right-hand side, we have a linear differential operator with the appropriate boundary conditions. We assume that the problem is well posed, meaning according to the standard definition, that there exists a function of kappa of t finite, such that the norm of the exact solution is bounded from above by this kappa function times the norm of the initial condition, where typically kappa is an exponent of alpha t times the coefficient. So Q will be our stable semi-discretization operator of the linear differential operator P, based on grid points and semi-bounded. So in order to further continue with our error analysis, we'll need to define the local truncation error. This is a standard definition. This is basically an error vector whose jth entry is defined as the difference between the smooth function applied to the grid point and applied to the linear operator, and the discrete operator applied to the projection of this function on the grid. So we have basically our semi-discrete approximation, a classical one, as follows. And in order to pursue with the error analysis, of course, the global error is defined as usual to be the vector, difference vector between the exact solution and the approximate solution projected on the grid. So this is a finite difference global error, standard one. So we can now derive an upper bound on the global error in some H norm associated basically with a discrete norm, and try to have an inequality. So we can prove that the norm of the global error in this discrete norm is bounded from above by a first term, which depends on the initial error times the exponent function, which is coming from the semi-boundedness of the discrete operator, and a second term, which will interest us, which is basically dealing with this function exponent of alpha t minus 1 divided by alpha times the maximum of our truncation error in this norm. So this inequality implies basically that the global error is at most of the order of the local truncation error. Usually the order is the same in the standard FDM. And this is one side of the Lax-Richtmeier equivalent theorem. So now the question is, can we get a better accuracy? In order to do so, we will have to have an expression of the truncation error fully developed. So this is what we need to do using Duhamel's principle. Indeed, the global error verifies the following differential equation. So using the classic Duhamel's principle, we get an expression for the global error. And we can see here that the second term basically is the effect of the homogeneous equation solution operator, S, on the truncation error and accumulation in time. So if we can get to the solution or to the situation where the norm of this truncation error applied to this solution operator, this norm is much smaller than the norm of the truncation error itself, then we get exactly the error inhibition effect. Meaning that the global error norm is smaller than the local error norm. So this is exactly what the block finite difference scheme is achieving. So the main problem that we took for the first analysis was the heat problem. Basically, we took it at first with periodic boundary conditions, and then we generalized the analysis to non-periodic boundary conditions, and then to higher dimensions of this problem. So the BFD team that was scheme that was built is a 2-point block scheme, and I will show that we got a 5th order scheme. So in each block, we take 2 grid points, one located at j minus 1/4 and one located at j plus 1/4. So the distance between them is half of h. So the second derivative in space is approximated by the following scheme. The first part is just the standard difference scheme, and the second part is the one that is built in order to enable us to find an optimized C in order to reach a better order. So this is the C that we are going to try and optimize. This scheme has been built on the requirement that we want the truncation error to be at least 3rd order. So this is what we are getting. We have 2 truncation error different at each node, but since the scheme is different, but basically there is a symmetry between them. The first term here is exactly the same in both nodes. And the second term, the one that is multiplied by C, is basically kind of symmetric. So a naive analysis would say that if we can choose the C to cancel the fourth order here and there, we'll get a better order. And unfortunately, this is not true. And because the optimal C is not found this way, we'll need to do and to provide a further analysis in order to find the actual optimal C. But the idea is that the highly oscillating third order terms will be dissipated and the fourth order will somehow cancel each other. So our objective is to find a C that answers this requirement. We find this C by performing a kind of standard Fourier transform analysis, but since Q cannot be diagonalized, we split the Fourier spectrum into low and high frequencies as follows. If omega, the mode omega is positive, we deduce n+1. And if it's negative, we add n+1. So we have two sorts of vectors, two kinds of vector. One vector depending on omega, and one vector depending on nu. And they have the following relations. So we build a full vector for each point and their adjacent nodes. And we are looking for eigenvectors, so-called eigenvectors, as the linear combination of the two vectors, one vector of omega and one vector of nu. So for the, excuse me? Okay. So for normalization, we are requiring that the sum of the square of alpha and beta will be equal to 1. So we are looking for two couples of alpha and beta, basically. So this is done after the expansion, asymptotically expanding for omega h very small. We get the following asymptotic expression of eigenvectors and eigenvalue. We input them in the approximated solution, and then we can look at the expression as the linear combination, basically, of the two vectors that we described earlier. So if we are looking at the first component, we can see that if we choose C to be -4 divided by 13, we can cancel this term, which is related to exponent of minus omega t square. And we can also notice that the second, the high mode eigenvector is basically multiplied with a term which is of fifth order. So basically our scheme will be of order 5 if C is equal to -4 divided by 13. But we will be able to exploit the fact that the error is highly oscillatory, and we can apply a filter, and then we will gain one more order of convergence. So this is basically the bonus of this analysis. So we found an optimal C, and the numerical results confirm this analysis. We can see here that the slope is 5 without post-processing, and with post-processing, this slope is 6. So we have order 6. The second part of the work is basically to establish the relation between DG method and BFD schemes. Based on Zhang and Shu's article for the first analysis of discontinuous Galerkin method, the nodal discontinuous Galerkin method is illustrated with the help of the one-dimensional linear heat equation with periodic boundary conditions and initial condition sinus x. But we also can, of course, illustrate it with other conditions. The scheme is built as a standard finite element scheme. We build a weak formulation, which is obtained by multiplying both sides of the equation by a test function v and performing integration by part. So this is the first phase of the construction of the scheme. Unfortunately, this is not stable, so we'll need to add other terms. The next step of the method is to replace the function u and v by piecewise polynomials degree of at most k. K is 1 in our case. We took linear polynomials. Since both functions are now discontinuous at the boundary point, j plus minus half, we need to introduce a numerical flux. The flux that was taken in Zhang and Shu's article is a central flux, since we are talking about the heat equation, and there is no direction in the flow of information, so a central flux can be chosen. This is not the only possibility. And the scheme needs to be stabilized, and we use Bauman and Oden penalty terms, which basically takes into account the value of the derivative of the test function at the boundaries times the jump of the exact function at those boundaries. So this is the first boundary and the second boundary. So this is the standard application of DG scheme. The matrix form is very simple and compact. Basically, we have an explicit vector of derivative. And on the other hand, we have a combination of 3 matrices, small one, 2 by 2, and very easy to handle, and very easy also to assemble the full linear equations. So we can notice that basically the matrix form has exactly the structure of the BFD scheme. So obviously, every nodal-based digit scheme can be viewed as a BFD scheme. On the other hand, we will need to show that a BFD scheme can be viewed as a DG scheme, and this is the more difficult part. So the proof is as follows. We start first of all with the first unstable formulation, and then we add penalty terms using the function and its derivative at the cell boundaries, exactly as it is done in the classical DG method. But instead of taking the central flux, we'll take a general flux. So we get also penalties and a general flux, so which give us 16 unknowns, and those unknowns needs to be determined. So from the requirements of stability, since we can use both analysis tools from the BFD method and the DG method. In that case, we used the tools developed for DG method for stability. We can determine all those unknowns. There is no unique solution, but at least we found one. And this full solution gives us basically the proof that the scheme, the BFD scheme and the GD scheme are equivalent. So we can enjoy basically all the advantages of both methods. The post-processing that was performed, as I mentioned earlier, is basically a one-time process, and we exploit the fact that with periodic boundary conditions, the leading term of the error is highly oscillatory. So we sort of cut off the high modes, and we gain one order out of the process. For not periodic boundary conditions, another filter was applied, also successfully. We also gained one order out of the process, but it was not done the same way. So the two generalizations that were made in this work, the first one was to move to Dirichlet boundary conditions instead of periodic. So we added a series of ghost points. In that case, we used the feature of the finite difference method. We added a couple of ghost points for every line and every column. And we interpolate with the help of those points. And then integrate this into the scheme. So this is working quite well. The implementation is seamless. And basically, we get exactly the same numerical results as for the periodic boundary condition. The second generalization was done to a two-dimensional heat equation with a Dirichlet boundary condition and on the square between 0 and 1. So a fourth Runge-Kutta scheme was used for time integration. So this is the numerical results that we got. Basically, the number of nodes on the grid is 2 times what is written in the title, since we have h divided by 2 distance. And we get, as expected, a 5th order with post-processing. So the generalization was made and fully implemented. As a summary, basically what we showed was that there is an equivalency between BFD and DG scheme for the heat equation model, at least. We succeeded in deriving scheme based on 2 grid points per cell, and were able to reach a 5th order method. So the method is quite efficient with a 6th order with post-processing. We succeeded in making the generalization to higher dimensions. And the future and undergoing work basically includes the analysis of hyperbolic equations and non-conforming geometric domains. So this is what we'll do next. So thank you very much for your attention, and I am available if you have any questions.
Thank you very much, Anne. We still have a few minutes to questions.
I have a question. Did you try discontinuous Galerkin, or you have just proved that it's equivalent? Did you see any benefit in the discontinuous Galerkin?
Basically, the tools, I didn't show it in my analysis, but the way we prove the stability of the BFD scheme is through the tools of the DG scheme. So we use the best tools that we have in hand from both sides of the methods. When it is convenient, we use the difference tools. And when it is convenient, we use the DG tools. So it is quite like enjoying both worlds.
Yeah. Okay, on the analysis part, it was very convincing. Just ask about the numerical experiments. So I understand that you've shown that it's equivalent, so you guessed that it should be the same.
Yeah, yeah. And the implementation basically is of the GG is as well very simple. So from this point of view of implementation, there is no big difference between the two methods because they are actually, the structure is exactly the same. But for example, for going to Dirichlet boundary conditions, it is easier to do it as a finite difference method.
Okay, thank you.
I have a question. What are the limitations of this method? Can it be applied with, let's say, diffusion with also a drift that has, you know, a drift that has a function, or in 2 dimensions?
2 dimensions, we did it, but only for uniform grids. What we need to do is basically to start working on non-uniform grids or grids, for example, where the boundary is not steady. So this is the work that needs to be done.
And can you explain intuitively why you only need to do the post-processing once at the very end? Why is it not beneficial to do it every, I don't know, T/4, you know?
Basically, we know that where the error is located. So this is the insight that we have thanks to our analysis. So the filter it is not so efficient because we need to examine all the points and to correct them, but we need to do it only once because at the end we know where the actual error is located.
Any more questions from the audience? Okay, so let's thank the speaker again. Thank you, Anne.
Thank you very much.
So
very much.
We have a few minutes till the third talk starts. We'll see you in 3:35.
Separate functions, also called multifunctions or shortly SVFs. This talk is an overview of our joint work with Niradin and Tel Zafarki from Tel Aviv University. And recent results are obtained in collaboration with Elena Berdisheva from the University of Gießen, Germany. So here are the short outline. First, I'll tell just several words on approximation of set-valued functions with convex compact images. We deal with multifunctions with general compact images. So I switch to this topic, and I will consider 2 main directions in approximation: approximation based on set operations and different direction, which is based on representations of multifunctions. In both cases, we consider our approach based on some metric stuff. And after that, I will switch to the notion of a new set-valued integral, which was introduced in us. And again, we use it in approximation of set-valued functions. So 2 words on motivation. In addition to the theoretical interest of this subject, various applications can be found in economy, optimization, game control theory, and differential inclusions, also in geometric modeling. for example, in geometric modeling, approximation of set-valued functions is related to the problem of the reconstruction of 3D object and 2D shapes from parallel cross sections. In this simple example, we can consider this 2D shape as the graph of set-valued function with 1D compact images. Some of them are shown as black lines. And just imagine that we want to reconstruct it from these values of a set-valued function. So some notions and notations I will need. K or D, by K or D, I denote the collection of compact sets, or D is the collection of convex sets. To measure the distance between sets, we use the Hausdorff distance. Here is its definition. These denote the distance from a point A to a set B. And we consider set-valued functions, univariate set-valued functions, mapping a closed interval to compact sets in RT. So the values of F are compact sets in RT. To present error bounds, I need some notions in metric space. We will do the modulus of continuity of a function F, just to recall its definition. Sometimes we consider functions which are Holberg continuous or Lipschitz continuous, and again, this is its definition. The notion of total variation is essential in our work. We consider functions that have bounded total variation. They are called BV functions. So again, here is its definition. Also, we use the notion of variation function, which is denoted here by VF. This is the total variation from A to X. And there is a connection between the continuity of a function F and its variation function. And there is the relation between their modulus of continuity. So if you don't remember some of things, I will recall it later. We consider approximation operators of the following form. They are linear, sample-based, with coefficients summing up to 1 in order to reconstruct constants. He is the underlying partition. Suppose that these operators approximate single-valued, real-valued functions with these error estimates. Omega is the modulus of continuity of F. The absolute value of He, we call it norm of He. This is the maximal distance between two consecutive points. And here phi is a general continuous non-decreasing in second argument function with 0 at 0. So in many operators, we have just a norm of phi here. And we want to adapt these operators to set-valued functions. And I recall that images of these functions are compact sets. So in adaptation to set-valued functions, there are two main approaches. The first approach is based on set operation. So here we have to replace operations between numbers by appropriate operations between sets. In the second approach, which is based on representations of set-valued functions, so first we have to find a representation of F by a collection of single-valued functions. And then the approximation of F is just reduced to that of representing single-valued functions. So this is the second approach. So, and the main challenge, main effort in this approach is to construct representations such that these representing functions inherit regularity properties from the original set-valued function. Since we obtain this, we obtain error bounds in terms of representing set-valued functions. So this is the main challenge. And in the approximation of multifunctions, we distinguish two cases. In one, set-valued functions have convex compact images. This case is easier. The second case, when multifunctions have general compact images, we deal with general compact images. So the first case is easier since we have two standard tools here. A classical set operation for for a convex set is the Minkowski linear combination. It is its definition. It is just a collection of all possible linear combinations of elements. So then we can adopt any approximation operator just by replacing linear combinations of number by these linear combinations of sets. And we have an adaptation. Another tool is a representation of convex sets by their support functions. Here is the definition of it. There is a one-to-one correspondence between a convex set and its support function. If A is non-convex, then the support function determine the convex hull of A. So it's this representation appropriate only for convex sets. And if we have representation for convex sets, we have representation for multifunctions with convex images, and we may construct an adaptation in the following way. We obtain operators on representing support functions. And many works done in this case. We can say here general approximation results. A is the operator of the form we saw before. It was adapted by this linear combination. An additional requirement, this operator is positive with non-negative functions. Yeah, excuse me. We needed to the approximant, I can see it, to be well defined, this positivity, and the error bounds are given in view of modulus of continuity of a set function. So that's what is done in the convex case. If we consider non-convex case, then Minkowski linear combination too big or is too big for this set. Shalom Nira. So let's consider this simple case, this simple set, which is non-convex, consisting of two elements, and we construct its Minkowski convex combination. It results with this set. So we can easily see that this set is bigger than A. This result is true in general for general compact sets. The equality we have only for convex sets. So this operation, this Minkowski average is too big for general sets. It was noticed by, for example, Vitali in 78 that Bernstein operators obtained by Minkowski linear, adapted by Minkowski linear combinations, they don't have approximate set valued functions with general images. And certain approximation, certain convexification phenomenon occurs. So this convexification phenomenon was formulated by Dean and Farkey in more general case for any approximation operators of the form we saw before with this additional property. Yeah, and it states that the approximant, the Hausdorff distance of the approximant and its convex hull, so you know the convex hull of this set, this distance tends to 0 as n tends to infinity. So this is a convexification when we use the Minkowski linear combination. So we need another set operation between general sets. This result was obtained by Dean and Farkey, as I said. And to introduce another set operation, first I want to introduce a new notion which is called a metric pairs of two sets. Suppose that we have two general compact sets. What is a metric pair? It's a pair of elements, A from A and B from B, such that these elements from these two sets, they are closest to each other, which means that B is a projection of A to set B or vice versa. So the collection of all these metric pairs we denote by pi. And in terms of these metric pairs, the Hausdorff distance can be written this way. And now in 1989, Sviarstein introduced a new set operation, which we later called the weighted metric average of two sets. We denote it by this sign. And in terms of metric pairs, it can be defined as follows. This is the collection of all linear combinations, but only of elements such that they form a metric pair from this collection. So we construct linear combinations only of closest elements from this set. Here is some property of this operation. We saw before that the Minkowski convex combination is too big. This set is included in this combination. In this case, we get the set A itself. And this is the famous metric property of this operation, which ensures, Einstein proved using this property that the set valued piecewise linear approximation converges to set valued functions with general compact images as normal partitions tends to 0. So this operation is binary operation and it is not associative. This is its lag. In this simple example, we can see just several methods for these two sets. They are shown as black thick lines. This is the set A and here the set B. And for different parameters of T, we obtain these sets. They are thin black lines and there are metric averages of these two sets. Okay, so as I said, this operation is a binary operation. And how to adapt this operator to our case of set valued functions. So the adaptation technique is as follows. Since it's binary operation, first we have to find a representation of an operator in terms of repeated binary averages. And then we replace these binary averages of numbers by this binary set operation, by the metric average. This is the technique of adaptation. So as example, we consider two approximation operators, Schoenberg-Spline operators and Bernstein polynomial operators. Here is its definition for the single valued case. There are two stable relation algorithms for Schoenberg-Spline operators, the Bohr algorithm and the Line-Riesenfeld algorithm for spline subdivision schemes. So for Bernstein polynomial operators, we have the Castellio algorithm. It allows to represent these operators in terms of binary averages. So we use these algorithms to adapt these operators to set valued functions. By Dean and Farkey was shown in 2001. They used the adaptation based on the Line-Riesenfeld algorithm. That they obtained the following approximation result for Holder continuous multifunction. And by Meade in 2006, we used the second algorithm from adaptation, the Bohr algorithm. And again, we have for Holder continuous function, the following approximation result. We have the conversion with the same rate here. But since these things are not so easy as we can think, for example, for polynomial algorithms, we don't have a general approximation result. We have it only for rather specific case of multifunctions with 1D compact images, all consisting of the same number of closed intervals. This is a very specific case. And for this case, we do have approximation result. We obtain it again for Holder continuous multifunctions. Okay, that's the adaptation we constructed, which are based on the metric average. The lack of associativity of the metric average is the reason why is so hard to extend it to 3 or more sets, this average to 3 or more sets. Anyway, we want to do it. So suppose that we are given a finite sequence of sets. First, I denote a new notion, which we call now a metric chain instead of metric pair. What is a metric chain? This vector is a metric chain if any two neighboring elements, consecutive elements, form a metric pair, which means that these elements from these sets correspondingly, they are closest to each other. So this is the requirement, and this vector we call a metric chain, and the collection of all this metric chain is denoted by CH. Let's consider this simple example. Assume that this is the graph of set valued function. Some images of this function are black lines. There are our sets, let's say AI. And in different colors, I depicted here different metric chains. Let's take, for example, this green metric chain. What we have to verify that any two consecutive elements, they form a metric pair. They're closest to each other. So if we consider these two elements from these two sets, they are closest to each other. Actually, they are the same. They're the same element. And again, we hear the same. We see it here and here, they are closest to each other. For this element from this set, the closest element is this one. Another option is this element, but let's say I picked up this one. So since this one is closest to this, they form a metric pair. And for this one, again, I'm looking for the closest element. Here is the closest element, and they form a metric pair, and I continue this way. We can also construct another metric chain. From here, I can take this one, they form a metric pair, and continue this. So when we construct many, many metric chains, this is our collection. Okay. So using the notion, we define a new set operation, which is called the metric linear combination of sets. This is how we denote it. This is its sign. And here is its definition. These are the linear combinations of elements only from the collection of metric chains. Only these elements we construct for them these metric linear combinations. So some properties. I would like to pay attention on this property, which is this property holds for compact set, not necessarily convex, for any real coefficients. The analog of this property in Minkowski sense, which means Minkowski linear combination, holds only for compact sets, which are convex, and with positive coefficients. Even for negative coefficients for convex sets, this property doesn't hold. In our metric linear combination, it's true for compact sets, not necessarily convex, and for real coefficients. So actually, this is one of the reasons why only positive operators are adapted for set-valued functions with convex images. That the convex combination holds only for positive coefficients. So that was written before that we need the positivity of operators. So we have a set operation. Now we can construct our adaptation. This is an operator we want to adapt, and we replace this combination of numbers by our metric linear combinations of these sets. This is our adaptation. And in 2007, by Dean, Parker, Mohawk, we get the following approximation result. No, it's just a basic error bounds. These bounds consist of two terms. This is twice modulus of continuity of f. So as norms tends to infinity, it tends to 0. It's okay. But the second term, in the second term, we apply this operator to piecewise linear single-valued functions, as phi, which interpolate this data, fi, their values from metric chain. So the approximation property of this operator depends on the way he approximates single-valued piecewise linear functions. This is the crucial term. And we consider some specific operators. As example, again, we take metric-Schoenberg spline operator. Here is its definition. It is our metric linear combination with coefficients. And we just specialize it on for Lipschitz continuous multifunctions. Here is our approximation result. Also for Bernstein polynomial operators, we have an approximation result. Here is its definition, the adaptation by metric linear combination. And in this adaptation, we have an approximation result for Lipschitz continuous functions with compact images in RD, in general in RD, and not only in R as in the adaptation by the metric average. So this is our error bounds. As an example of non-positive operators, we consider interpolation polynomial operators in their Lagrange form. Here is our definition again with the metric linear combination. And again, we show that for Lipschitz continuous multifunctions, these operators with underlying partitions consisting of roots of the Chebyshev polynomial, we have the following approximation results. So that's what is done with metric linear combination. And here are some examples of these set-valued interpolants. In this example, we interpolate 3 compact sets in R, which are not convex. Now this set is in the middle is convex, but these 2 sets are non-convex. Using our definition we saw before, these graphs are parabolic interpolants of some metric chains. So here we just increase number of parabolic interpolants. This is our butterfly, as we call it. And in this case, we interpolate convex data. This is a convex set. These 2 sets consist only of 1 point. So in general, it's convex 2. And again, these graphs are some parabolic interpolants. And here we have more parabolic interpolants. This is the fish set value. Okay, the next example was recently obtained by a student of Miradin and David Levin, Hossein Zafar. They started to work on a efficient calculation of set-valued polynomial interpolation. So they interpolate this function, they approximate this function. The graph of function are shown in this picture in yellow. Actually, it's a mustard color. In blue, we see cross-section of the interpolants. In this case, they use 5 interpolation points, which are roots of Chebyshevs. And in this case, we have 25 interpolation points. So this approximation is much better, of course. Here we see the graph of F between the cross sections of the set valued interpolant. Okay, so this is just to see how it looks for 1D sets. We also approximate non-continuous set valued functions, again with the same adaptation. It is our metric linear combination. For this case, we consider only local operators, so we have this additional property. And we managed to prove, this is our result with Elena Batisheva from Germany, that for multifunctions of bounded variation, we consider multifunctions only with bounded variation, we obtain the following approximation result. So if the function is not continuous, then we measure the distance in an averaged Hausdorff distance. And here we have the variation is involved, the norm of he and c depends only on the operator. Here is a very general approximation result. And again, we specialize it for Schoenberg spline operator. This operator is symmetric, so we consider symmetric Schoenberg spline operators. It is our definition with metric linear combination. And that is what we have for functions with bounded variation for this operator with our estimates. Okay, the second example, which we consider the Bernstein polynomial operators, again, its definition, these operators are not local, but they do have a certain localization property due to the following result of Lorentz. The result, these coefficients are not zero in this operator, but they are small. So we can control these coefficients. And also for this case, we have the approximation results as it's some natural number. And again, what is done here, all stuff are based on our new set operation, the metric linear combination. Okay, it was one direction, which is based on set operation. Another direction is based on representation of F into PU, the representation by selection. By selections, what is a selection of multifunction? Here is its definition. It's a single valued function such that its graph stays in the graph of F. That's a definition in general. So in this representation, these functions are selections. As I said, the main challenge we want to construct such a representation that these selections inherit regularity property or from F. And here is our construction. Again, we use the tool of aromatic chains. We are given F, and here is a partition, and here is a metric chain. And first, we construct a piecewise constant multifunctions. We call them chain functions. Definition. And now, what is a metric selection? A selection S is a metric selection if there is a sequence of these chain functions with this additional property with non-standing to zero as k tends to infinity, such that this sequence converges pointlessly to S. S is our selection. So this is the definition. Now, what we know about this metric selection? Again, all properties which are stated here are for functions with bounded variations. We show that through any point of the graph of F, there exists at least one metric selection. So we have immediately a representation by these metric selections. We also prove they do inherit the regularity property of F. They have variation bounded by those of F, and they inherit the modulus of continuity of variation function. But there is a connection between the variation function and F itself. So in particular, if F is Lipschitz, then their metric selections are also Lipschitz with the same constant. So they're good in this sense. And now in this example, we can see two simple metric selections for very simple set-valued functions with 1D images. The multifunction, its graph is in gray. This series of black dots, it is just one metric chain, and we construct chain functions, and we go to the limb, and we result in this metric selection, which with graphs in blue. And we have another metric selection, again, another metric chain, and we increase number of interpolation points, points in partition, and end up with this metric selection, which is discontinuous here. So since this function is also discontinuous in the Hausdorff distance. And what is written here, it's a kind of graphical property of this selection. We also call them lazy selections if they try to stay as constant as possible. Okay, so once we have this representation, our adaptation just to apply an operator on any selection in this representation. We have this representation. And here is a very general approximation result, which was obtained in 2011. If this operator approximates single-valued functions with these error estimates, then we prove that for multifunction, which is a continuous and or bounded variation, we have the following approximation result. And again, it can be specialized for different operators. And just how many minutes I have, several words on the new notion of set-valued integrals, how we use our metric tools to introduce a new notion of set-valued integral. This is a classical notion of set-valued integral, which is called the Oman integral. Its definition is written here. This is a collection of integrals of all integrable selections. The main property is that this integral is always convex. Even this function has non-convex images. So this is like for this special case. And now we introduce our definition. First, within our metric linear combination, we construct a sequence of metric sums. This is the metric sum. This is our definition, the values of f with these log coefficients. We construct this sequence with norm, and we consider sequence with norm tending to 0. And the metric integral is defined to be the Krotowski upper limit of this sequence of metric sums. The Krotowski upper limit of sets, which consists of all limits of convergent sequences, which is written, this is just a definition of Krotowski upper limit. So this is a definition. So what we can say about this integral, again, all stuff here are for functions of the bounded variation. This set is closed, and it's not also necessarily convex in contrast to the Oman integral. Here is the relation between the metric integral and its metric selections. It's just a collection of integrals of all metric selections. And this set is smaller than the Oman integral. Even convex set is a subset of the Oman integral. And we have equality for this special case. And also some analogous of first fundamental theorem in calculus we have here. So it's not so important for approximation. And now we want to use it again to approximate set-valued functions. We consider non-continuous set-valued function, and we define set-valued Stiklov function, which is also called metric. This is the definition of Stiklov function in the single-valued case, and we extend it by using our metric integral, such obtaining a metric Stiklov set-valued function. And following properties of the metric integral, we show that it can be represented by Stiklov functions of metric selections. We have some nice properties. And here is the approximation result, which was obtained in collaboration with the random partition. Okay, that's what is done in non-convex case. In just 2 words, what we obtained recently, our next step is to extend this integral to the weighted metric integral with this weight function. We use this metric, weighted metric integral to define the metric Fourier series of a set-valued function via the integral representation with the Dirichlet kernel. So we use it to obtain analog of Fourier series. We derive error bounds, and what is interesting, we proved that this metric Fourier approximants of f converges pointedly to the values of f at the points of continuity. That's our main result. So this just was in last paper, which we submitted 2 weeks ago, and it was found in archive. So that's what I wanted to share with you. Thank you.
Thank you very much. We have
Questions?
Yeah, 2 minutes for questions.
Sorry for taking more time that I have.
So maybe I would ask.
Yes.
Do you have any analog for the average of more than 2 elements, like we do on, say, the Frechet mean or Kircher mean, something that will minimize symmetric or metric squared or something like that?
No, our average is the metric average, and for any number of sets. But this is the usual with no minimizing property.
Okay.
The minimal is the distance between two consecutive elements, that's all, metric pair. So in the metric, we use only Hausdorff distance. This is our metric.
Okay. Maybe one more question? Oh, okay. I think we almost run out of time.
Yeah.
So thank you again, Alana, for the interesting talk.
Thank you again for the invitation. Okay.
All right, so I should give the token to Jeremy.
Yeah.
And,
can you give me the screen?
Yeah, so
Great.
you have the spotlight. I would just start by I don't think that you need a lot of introduction, but last and definitely not least is Jeremy, Professor of Mathematics from Bar-Ilan University. Jeremy is pretty active in the community of the applied math, so you probably know him or talk with him, and it's a pleasure to have you here. He's an expert on mathematical physics, differential equations, numerical methods, and many more. And today we're going to talk about the KP complex. So let's hear more details on that.
Okay. So can you hear me? Nir, can you hear me?
Yes, loud and clear.
Good. Okay. That's the first thing to check. So I apologize for giving a title that is not really possible to understand. If I'm not mistaken, the first time I gave a talk at the Israel Math Union in 1995, I also gave a talk on the KP equation, which is the Kadomtsev-Petviashvili equation. I think back then, most people in applied math knew what it was, but I think today not. So I'm going to spend most of this talk explaining what the title means. I'll explain what KP is, what KP reductions are, what the KP lattice is. Because this is a short talk, I don't think I'll have time to put this in the bigger context. So I didn't try and do that at the start. I just wrote one slide at the end to remind myself to try and explain a little bit of the larger context and why we're trying to do this. So I should mention that this is joint work with my longtime collaborator, Sasha Racine, who is in Ariel. Okay, so let me try and introduce what the KP equation is and how it first came about. So if you haven't heard of KP, you might not have heard of KdV, but I certainly know some of the audience have heard of KdV. KdV is the Korteweg-de Vries equation, was first studied about 125 years ago now as a model for solitons. Solitons are solitary waves. So waves where you just have a single lump as opposed to repeated lumps in a typical sine or cos wave. Now, here we're talking about a function u of two variables, t and x. So t is the time, and x is the space variable. So this describes the height of the wave as a function of space and time, where it's a one-dimensional wave. So it's moving in one dimension, x, and x is the coordinate, the relevant spatial coordinate. So the remarkable thing about this equation is that it has soliton solutions. So soliton solutions are solutions that go to 0 at plus or minus spatial infinity, and they just have a lump in the middle. And what do these look like? These look like 1 over cosh squared. So cosh is, of course, 1 at the origin and goes up to infinity. So this is something that at where the argument vanishes, where x equals 4b squared t, this has its peak, and it decays as x goes to plus or minus infinity. B here is a parameter, and you can see that B is, it's the height, because, well, B squared is the height. B is also 1 over the width, and B squared is also the speed. So you notice that in this version of KDV, the speed of the wave is always positive. So it's a unidirectional soliton. It can only go in one direction. So now we want to ask, if we're in a setting where there are 2 spatial dimensions, x and y, so this is a solution that is independent of y, but suppose now we have some perturbation in the y direction. Will this wave be stable? So this was studied in a paper by Kadomtsev and Petviashvili in 1970, and it's easy to do. It's linear perturbation analysis, where you look at this solution and you ask, is it stable under a simple harmonic, harmonic in time, harmonic in space perturbation? And you find that the amplitude is governed by this equation, where phi is a new function which is related to u by phi x equals minus or plus c over 2 uy. So the sign here, the c here, represents the speed of the harmonic perturbation, and the minus or plus depends on the dispersion. So does the phase velocity of the wave increase or decrease as a function of wave number? And they found the critical result, that is, in the case of negative dispersion, these waves are stable against transverse perturbations, and in the case of positive dispersion, they're unstable. Okay, now this equation, so it's nice to get rid of phi. So how are we going to get rid of phi? If we just differentiate both sides with respect to x, then we're going to get an extra x derivative over here, but we'll get phi yx, which we can then replace by u yy. So I've introduced normalizations I prefer. This is a standard way you'll see the KP equation in the literature, and there's 2 signs. The positive sign is what's called KP2, which is where KDV solitons are stable. The minus sign is KP1, where KDV solitons are unstable. Okay, so another way we often look at this is we introduce a potential function Q, and if you do that, you can integrate this once and you can write it in this form. And so this was found in the context of perturbation of KDV solitons, but in fact, it exhibits much more general solitons. It exhibits solitons not just traveling in the x direction, but in traveling in an arbitrary direction in the xy plane. And that's given by these functions here. So again, B is an arbitrary parameter, V is an arbitrary parameter, and you can have these general line solitons and remarkable interacting patterns of these. So just to give you a few pictures, so this is a picture that was taken by Mark Ablowitz. So you can see here what is basically 3 line solitons. It's not exact, right? There's one here, and a third one interacting like this. Here's another picture of the same thing where you can see the line solitons forming a rather nice A. Now, if I manage to get out of my full screen, I'll show you quickly a video. This was sent to me by my colleague Gil Ariel. He took this at the beach. I forget where. Gil, are you listening? Where was it? Oh, not listening.
Someplace very exotic, Tel Aviv.
Tel Aviv, okay. Here you see these line solitons. So now here there's 2 that are about to collide and go through each other. Okay, so you see these single line solitons coming together. I'll play it one more time. it's a bit of a mess at the start, but there's a particularly nice example of two colliding solitons. That wasn't it. It's about to come now. No, that's not what I meant. Where is it? Yeah, here they come. Two lines colliding, going through each other, then meeting other ones. Those are solitons. Now, I have to admit, this is not KDV solitons, because these solitons we saw here in the picture were actually unidirectional, but they were going in both directions. So that's definitely not KDV. Okay, let's go back to this. Let me see if I can get full screen again. Yeah. Okay. So that's how the KP equation first arose, but rapidly people found out that there were many other applications of KP, and it's still actively studied today in a lot of theoretical contexts, but not just for PDE applications, but also applications particularly in geometry. So I think the most exciting application of KP, and the thing that best showed its universal nature, was a theory called Sato theory. So Mikio Sato, I understand he's still alive. He must be very old by now. He was a founder of a very large school of Japanese mathematicians who came up with the theory of isospectral deformations of differential operators, which is now called Sato theory. So in Sato theory, we look at an nth order differential operator in one variable, x. So this is a general nth differential operator in one variable, x, sorry. And now we can do some normalizations here. By changing the independent variable, we can take the leading order coefficient to be 1 without loss of generality. And by conjugation, this is an operator. So this is operator conjugation, but conjugation by a function, we can make the leading order, the 1 from leading order coefficient to be 0. So we always take u0 to be 1 and u1 to be 0. Then that's what's called a monic nth order differential operator. Now, when we study differential operators in different contexts in mathematics, possibly the most important thing we're looking at is the spectrum of the differential operator. Now, of course, it's very different for odd and even order operators, but in some sense, so one of the things we want to do is to know, if we have a differential operator, how can we perturb it in such a way to keep the spectrum the same? Now we by spectrum. So we're looking for the spectral deformations, or ISD, of the operator. Now, the Japanese school, Sato, noticed that you could study this as follows. Instead of looking at P, you take an nth root of P. You can find a pseudo-differential operator. So a pseudo-differential operator always looks like this. Its leading order term is just D, is just the partial derivative with respect to x. And it has an infinite tail of negative order terms. How do you define the negative order derivative? It's defined by integration by parts. As if I wanted to, multiply this by a function and I integrate by parts, I'd move the D inverse over, and it would never stop. I'd have to repeat it. So this is how the D inverse operator is defined. So Sato and his group found that instead of studying differential operators of order n for different n's, it was in fact sufficient to study one universal object, the first order pseudo differential operator. And here's the main theorem that says the general isospectral deformation of L, and I'm not telling you exactly what an isospectral deformation is, how it's defined, but the general notion should be clear. The general isospectral deformation takes the form of this, dl dt, so this is a differential operator, is a commutator of two differential operators, Q and L, where Q has to be, now L is pseudo-differential, but Q is actually differential. And it's the span of 1d L squared plus L cubed plus, what does this plus mean? This plus means, so L is a pseudo-differential operator of order 1. I take the square, it has order 2, I take just the differential part. That's what the plus means. So I can take any Q, I take any deformation of L. So now I'm adding a parameter T. T is my deformation parameter. I look at this equation. This gives me an isospectral deformation of the operator L, and I can then push it back to the original nth order operator P. Okay? Now, not only does this specify all the isospectral deformations, but it turns out these that are the generators of the isospectral deformations are, in fact, they generate flows that commute. So in fact, I can look at an infinite string of different flows where dl dtm is simply defined by the commutator of the positive part or the non-negative part of Lm with L. And I can look at these for all M. Okay, so first of all, M equals 0 and M equals 1. M equals 0, this just means because if I take 0 here, then that's just 1, which commutes with everything. So that means that I just can take everything independent of T0. I can ignore T0. T1 can be identified with X. So the first interesting coordinates here are T2 and T3. So if you look at these differential operators, it's a simple consequence of this equation here. This is called the Lax equation, that these differential operators satisfy this thing, which is called a zero curvature condition for reasons I won't explain. But if you take the simplest zero curvature condition for M and N being 2 and 3, so this is a second order monic differential operator. This is a third order monic differential operator. You stuff these two in this equation, you find that V and W are determined in terms of U, and you find that U should satisfy the KP equation. So the KP equation, which I showed you to be relevant in terms of waves, in fact has this interpretation. It's the first of, now we can do this for any N and M, so it's the first of an infinite hierarchy of deformation equations describing isospectral deformations of differential operators. Okay, so that's KP. What do I mean by KP reductions? So it's a remarkable fact that KP, which, you look at KP and you say, well, this looks a bit odd, this equation. I could sort of add some extra terms in here by doing translations of U and X and T, make it look a little more general. It doesn't look like a particularly general equation. But so first of all, we know that if we drop the Y dependence, then we go back to KdV. That means there's no perturbation in the Y direction, we go back to KdV. If we drop the T dependence, then we get another well-known equation called the Boussinesq equation, which in fact dates back to even earlier, to the 1870s, even before KdV. Usually the Y here is written as T. Then this is also an equation that arises in describing waves in fluids. And this is in fact the lowest order equation that describes, if this describes unidirectional solitons, the Boussinesq equation describes already bidirectional solitons. They can go in both directions. Okay, so both of these equations arise as reductions of KP. And in fact, you can check that how do we get these reductions in KP? Well, we set there should be no dependence on one of the coordinates. So that's what's called that's a symmetry reduction, because the whole system has a translation invariance in these coordinates. I didn't ever write any of the coordinates explicitly. There's symmetry reductions that I impose that there's no dependence on T2 or T3. I can similarly do N reduction where there's no dependence on Tn. But it was a great surprise when people started finding that KP includes many other reductions. So to introduce the other reductions, I have to look at what's called the linear system associated with KP. So that's these equations here. So if you look at these two equations for psi is known as an eigenfunction of KP. So this equation, it looks like as we've written it here, it looks like a sort of deformed heat equation. I've done it for KP2. If I did it for KPY, there would be an I here. So this is usually referred to as a Schrodinger equation, even though it's in this setting, it's actually a heat type equation, excuse me. And here is an equation psi t. You'll notice these are both linear equations. If you look at the consistency of these linear equations, so I'm here telling you what the evolution in the y direction is, here what the evolution in the t direction is. The cross derivatives have to be equal. If you impose the equality of the cross derivatives, you find that Q has to satisfy the potential Kp equation, maybe up to some kind of translation. So this is a linear system, the consistency of which implies Kp. It turns out there are two such linear systems. There's another one where the sign of y is reversed. The original Kp was symmetric under changing the sign of y. And so here I've just changed the signs of all the derivatives of y. And this system is called the adjoint Kp linear system, and solutions are called adjoint eigenfunctions. So if we consider the system with just one eigenfunction, so I've written the system for an eigenfunction and I've written Kp, lo and behold, it is consistent to take Q equal to psi. If I take Q equal to psi, then here I have equations for psi, and I plug those into here, and it turns out the equation is satisfied. Right? Now, this is something that doesn't have an immediate explanation. Not only is this equation satisfied, it comes out to be a very nice equation, a standard equation, the Burger's equation. Some of you might prefer to call this the viscous Burger's equation. The non-viscous equation doesn't have the second derivative term here. This was found by a Japanese mathematician, Harada, in 1984, but it certainly wasn't known widely in the West. And Chakravarti and Kodama in 2009 wrote a long paper about how Kp can be reduced to the Burger's hierarchy and consequences of that. It doesn't end there. Let's take a system with one eigenfunction and one adjoint eigenfunction. So here's the adjoint eigenfunction, here's Kp. It turns out it's consistent to take Qx equal to psi star. And I have to tell you what Qy is, so you can check that consistent with this is to take Qy equal to this. And then the first and third equations here become a real form of the nonlinear Schrodinger equation. Again, if you put I, you would have exactly the nonlinear Schrodinger equation and its complex conjugate. Okay? You can also here apply this reduction to the T equations. You get this system of equations which are called coupled modified KdV systems. These systems have been studied, particularly nonlinear Schrodinger equation, of course, has enormous applications. The reduction of Kp to what's called the AKNS hierarchy, which includes all these equations, is due to Konopolchenko, Sidorenko, and Stramp in 1991. And they found it as a symmetry reduction. I won't explain in what sense it's a symmetry reduction. Cheng and Li found out how to do this in the context of Sato theory. They saw that the pseudo differential operator should simply be taken in this form. And this allowed them then to guess many other forms of the pseudo differential operator, which you can consistently impose and get other reductions. So this NLS reduction is understood because it arises as reducing with respect to a symmetry. But I would emphasize that the Burger's, as far as I'm aware, is not understood as reducing with respect to a symmetry. And in general, there are papers from consistently over the last 20 years finding more and more reductions of Kp. There are also generalizations of Kp, and these need some explanation. Okay, so we're getting there. What is the Kp lattice? Okay, so for this, I need to introduce a new object. So Kp has what's called a Bakeland transformation. So a Bakeland transformation is a way of taking a solution of a PDE and finding another solution by solving a simpler PDE. So in the case of Kp, it's simple to state. If we have a solution of, I work here with potential Kp, And then we take an sorry? Okay, no. If we have a solution of Kp, and then I take an eigenfunction of associated with that solution, I remind you that the eigenfunction satisfies this equation. So if we know Q, the eigenfunction, of course, depends on Q, but this is a linear equation. I can solve it if I know Q. I have many tools available to solve it. So then Q plus 2 psi x over psi is also a solution. Right? So this was discovered by, so I write his name here, Chen in 1975. He also found that, in fact, if you have two eigenfunctions, psi1, psi2, then Q plus 2wx over w is also a solution, where w is the Vronsky of psi1 and psi2. Psi1, psi2x minus psi2, psi1x. So this is a way of constructing solutions starting, if you have an initial solution, you can generate more solutions. A much more extensive result of this kind was proved by, I believe, Freeman and Nimmo for the first time in 1983, that if you have n eigenfunctions associated with a solution, then you can take Q plus 2wx over w, where w is the Vronskian, and you still have a solution. There are many proofs of this available. Now you have to do lots of manipulations with determinants, and it's a lot of fun. Okay. So I would mention that if we just take the trivial solution, Q equals lambda x, where lambda is a constant, then the general eigenfunction, so that makes the, you can write down a general solution of the eigenfunction equation, and it's a superposition of waves of this sort. So I write it as an integral rho k dk of this kind of wave. Rho k dk is any kind of measure here. So in fact, I could take a point measure, a continuous measure, whatever I want. So using these eigenfunctions, I can get a huge, vast range of solutions. This has been used in recent years to, the pictures that I showed you were from a paper of Chakravarti and Kodama, where they solved the inverse problem, where they said, if I have a particular pattern of waves I want to see, how can I find a solution to give that pattern? Okay, so now Hirota, who is another big name in this, also from the Japanese school, he passed away a few years ago. Hirota made the following observation, that if we start with an initial solution Q, and we have three eigenfunctions, psi1, psi2, psi3, well, we can build solutions. We can use one of the psis to get Q1, Q2, Q3. We can use two of the psis and the Vronskian to get Q1, 2, Q1, 3, Q2, 3. Or we can use three of the psis and the Vronskians to get this. So these solutions, well, in fact, Q1, 2, 3 doesn't appear here, but these six solutions, the six solutions Q1 up to Q2, 3 are related by an algebraic equation. This is called the Hirota equation. Now, the way people think about this is that they think of each of these solutions as a point on a lattice. So there's a point corresponding to each solution. And whenever a solution can be generated from an initial solution by a Bakelin transformation, we connect those 2 points. So here you naturally have a cube. Q is connected to Q1, Q2, Q3, which Q1 is connected to Q1, 2, Q1, 3, Q2 to Q2, 3, Q1, 2, and so on. You have a cube. So it's natural to continue this and to look at an equation for a quantity QNMP. We're now forgetting the XYT dependence, but we're just looking at a scalar function on a Z-cubed lattice, and it should satisfy this at every point. So this is what's called the discrete KP equation, which it's sometimes called the Hirota equation, sometimes Hirota-Miwa, sometimes discrete KP. This is the equation it has to satisfy. This relates, if we're looking at the function as a function on the three-dimensional lattice, this relates the solutions at 6 different points. Excuse me, I'm just going to look at my clock to see how much longer do I have, Nia? Minutes, right? Okay, don't worry.
Okay.
Okay.
3 or 4 minutes. Yeah.
Okay, so the standard KP lattice is this thing here, is the Z cubed lattice, where associated with each point on the lattice you have a solution. We want to suggest that now I'm going to get to my point, and I can use whatever time I have left to show you examples if needed. We want to suggest that this is maybe not the best way about thinking of Bakelin transformations of KP. And the reason for that is that in a Z-cubed lattice, we have a distinct, now if we move from one point to the next, we have a notion of when, so then you can move from the point you came to another point. We have a clear notion of when those points are collinear. And in the case of KP, there's no notion of what it means to repeat the same Bakelin transformation. There's another reason as well. So I've mentioned all the Bakelin transformations to do with eigenfunctions, but there are also Bakelin transformations to do with adjoint eigenfunctions. So the inverse of a BT associated with an eigenfunction is a BT associated with an adjoint eigenfunction. Furthermore, in the same way that you can superpose two BTs, you can superpose a BT with an eigenfunction associated with an eigenfunction and a BT associated with an adjoint eigenfunction. Here are the equations here, but note that it's not quite explicit. Whereas in the formulas I had before, I had WX and W here, where W was the Vronskin of psi1, psi2. Here I have to solve a system of differential equations for C. This is a trivial system to solve. I just integrate, okay? And these are all consistent. So I have exactly one constant to fix. Okay, so I wrote before this, that if we have a solution Q and 3 eigenfunctions, we can build 3 new solutions. 7 new solutions like this. So similarly, if we have a solution Q, 2 eigenfunctions and 1 adjoint eigenfunction, we can build new solutions like this. -1 is doing the adjoint Bakelin transformation associated with the adjoint eigenfunctions. We know there will be constants associated with C1, C2. So I don't want to explain the last lines on this page. I want to jump straight to the first example. So you can restrict. We know that KP can be reduced in many ways. We want to suggest, and it seems a reasonable working hypothesis, that all these restrictions of KP can be obtained by requiring invariance under a single lattice translation. So here, for example, if we have 1 eigenfunction and 1 adjoint eigenfunction, I can impose the invariance that Q1 minus 1 equals Q1. You sort this out, what this condition means, and without going into the details, you get the Burger's equation. I'm jumping from page to page. If you have 2 eigenfunctions and 1 adjoint eigenfunction, and you impose this invariance, you get a system that looks like NLS. It's in fact a system called the 2 boson system, but is related by a simple change of coordinates also to NLS. KdV also you get, KdV in fact only requires eigenfunctions, and to impose Q1, 2 equals Q. There's some details here that I'm not going to go into because I want to finish on time, that in fact you get something called the Ur KdV equation. Ur is a prefix in German meaning the fundamental KdV equation, which is, it's this, it's this equation here, psi t equals this. And if you take psi that satisfies this and compute the Schwarzian derivative, you can check that the Schwarzian derivative obeys the KdV equation. This is to do with SL2 invariance. The Schwarzian derivative is the simplest SL2 invariant. So here the choice of psi1, psi2, I was just, these have to be linearly independent, but I can make a change of basis and it shouldn't change anything fundamentally. So we naturally get an SL2 invariant system. So what I've outlined to you here is that a rather better way we think of thinking of lattice KP is that you have a single solution and you have many possible eigenfunctions and many possible adjoint eigenfunctions associated with the solution. And the way to construct reductions is to impose equations of this sort, that 2 points on the associated lattice, I can only make one Bakelin transformation corresponding to each eigenfunction I have. So I impose, if I have one regular and one adjoint, I can find what Q1 minus 1 is. If I have here, I could have Q1 minus 1. Here I could also have Q2, 1, 2 minus 1 equals Q. There are many other possible reductions here. It seems to us that a large amount of reductions appear this way. We are certainly nowhere near proving that all the reductions known of KP appear this way, but this is a very logical way for reductions to come. I'm going to skip the rest of my slides. I do want to say just 2 words that this arose in the study of the relationship of Bakelin transformations and symmetries. And we found that this is a wonderful organizing system to organize the Bakelin transformations and the symmetries of the underlying systems. But that has to be a subject for a separate talk. So thank you to the organizers of the IMU Applied Math meeting. And thank you to those of you who are listening. Thank you.
Thank you, Jeremy. Any questions from the audience?
Okay. That either means it was all understood or it was all completely not understood, which is just fine.
All right. Maybe people need some time.
Okay.
Anyway, yeah, I also like to thank again the organizers, Dalia and Adi. And I also want your attention to the afternoon session. So the conference is not over. There's some plenary talks and also a lightning session. Also tomorrow morning noon. So if no further questions to Jeremy, thank you all for coming. It was a pleasure, and we will announce the video. Hopefully it will be available sometime soon.
Thank you, Nir.
Thank you.
Thank you.
Thanks, Neil.